Hello everyone, my name is Akanksha Kapil and as a part of our course Foundational Model and Generative AI, I will be presenting a paper called TokenSkip, Controllable Chain of Thoughts Compression in LLMs. So first is the introduction, then I will explain what is chain of thoughts and the methodology and the algorithm of the paper, the limitations of the paper. So what is chain of thoughts? Chain of thoughts is not just a prompting technique. It is a reasoning paradigm. It refers to the sequence of intermediate reasoning steps that a model generates before arriving to the final answer. So think like a student solving a maths problem here. So we just don't write the answer. So first we solve it step by step and then we come to the answer. We know that from research that generating these intermediate steps significantly improves the accuracy in the maths, logic, and complex tasks because it allows the model to debug its own thinking as it goes on. Let's take an example here. So, this is a maths problem. So Marcus is 5 years younger than Dina, and Dina is 26 years old, and Marcus is half of the Leo's age. So what is the age of Leo? So here we first solve step by step. First we write that Dina's age is 26. Then we write that Marcus is 26 years matlab 5 years younger than the Dina. So 26 minus 5, 21, and uh, Marcus is half the age of Leo. So Leo equals to 2 into 21. So that is 42. So these are the step by step process which we follow in the chain of thoughts. So this entire block of text is the chain of thoughts. While this logic gets the right answer, we notice that it has many intermediate text also, like the verbose. So standard chain of thoughts responses are incredibly redundant. The model generates token which means therefore and repeat numbers unnecessary. So why this is a problem? So slower inference. LLMs generate text one token at a time. So if the reasoning takes 300 tokens, so it will have 300 sequential tokens, 300 sequential operations. And the second problem is memory usage. The longer sequence fill up more cache memory. And the cost, ultimately you are paying for every token generation, so the cost will also be higher. Because of the standard issues in this COT. This brings the motivation of our paper, that is the compression of COT. So we have trade-off. We need the reasoning steps of accuracy, but the length of these steps kills the efficiency. So the author asked the key question: do we really need all the sequence of steps or single word in the reasoning chain here? Or we can skip some certain words or just keep the logic of the answer. So this motivates the token skip, a method that compresses the reasoning response itself. Then comes the overall methodology. So here what we are doing, uh, we take the standard LLM and generate full long reasoning chain here. Second step is we take a separate tool to analyze the output and estimate the importance of every single token here. We select the compression ratio as gamma and prune or delete the tokens that are not important according to the percentage of the gamma. Crucially, then we fine tune the LLM on the compressed version or the shortened data, and the goal is to teach the model the to the output these compressed version natively. So this is the main inference. So first the diagram visualize the process. On the left you can see during training you notice that we don't touch the questions. We take the COT response and pass it to the compressor. The this removes the filter या filler words and create a compressed COT. Then we train the model to map the question directly to the efficient output. On the right, during the inference, the user simply provides the question and the compressed tag. The fine-tuned LLM directly generates the short and efficient reasoning step. The this skips the verbose if matlab efficiently, matlab automatically. So the matlab words like therefore and all are skipped automatically here. Then comes the token importance estimation, like how are we calculating the importance score. So how does the compressor decide what to cut and what to not? So this completely rely on LLM Lingua 2 model, a small bidirectional language model. So it looks fully on the reasoning chain and assign the importance score to each token. The key observation here is that the distribution is highly skewed. The number of tokens carry the core logic while a vast number of tokens have low contribution. This confirms COT responses are not fully waste, but they have certain kinds of important values. This is the normal pruning algorithm. So first we compute the importance score of the every token it is generating. We determine the threshold based on the parameter gamma. Suppose we have taken 40%, then we separate the top 40% of the important tokens and then create a new reasoning chain keeping only the tokens that are above that threshold. We then train on the optimized COT and get the sequence of answers, the final sequence of answers according to our compressed COT. Then comes the experimental setup. So to validate this, the authors did rigorous experiments. So they used Llama 3.18b and larger Quen 2.514b. They tested on maths dataset, that is GSM 8K and maths 500. They measure how the tokens count dropped versus how the accuracy changed. So how the masked, how many masked the as in when we mask the tokens, how the accuracies are changing with respect to the models. So this is the graph of compression versus accuracy. So here the graph is most important is the result of the paper. So the x-axis shows the number of reasoning tokens, lower is the compressed, and y-axis shows the accuracy. The green line here you can see here, notice how flat it is. Even we have reduced the reasoning tokens from 325 to 175. Here, the accuracy stays almost perfect, 93 to 94%. This proves that the cut of almost half of the tokens without the model's logic. So, summarizing that, the quantitative result when for Quen 14b model, we achieve when we do 40% of the reduction in the token lengths in the reasoning chain, only 0.4% is getting changed. And for the smaller data, Llama 8b, 30% of the trim results, your trim reasoning shows 4% drops in the accuracy, but it provides 1.4x speed in the inference. Basically, you get the same smart answer but in a faster way. So these are the key findings which I explained in the graph slide itself, that when we do 40% of the COD 40% of the COD trimming, the accuracy is just decreased by 0.4%, and in the Llama when we do 30% of the trimming, the 4% accuracy drops, but the speed is also good, like 1.4% of the speed is increased here. We also have some limitations here. So of course no method is perfect. So the here the limitation is that the evaluation is done on maths based tasks. We don't know how well it will transfer on the creative writing datas, or where we have a lot of words like this, therefore, and all on that kind of data. Then the second is the importance matrix. We have used model LLM Lingua 2. That is a generalized tool, and it is not specialized for any reasoning chains, so it might be not that optimal. Then comes the compression parameter. The compression parameter isn't automatic. We currently require it currently requires us to choose the right level of the compression manually here. So the conclusion is that TokenSkip offers a robust method for controllable chain of thought compressions. It successfully reduced the length of the generated responses, and therefore the cost and the latency, while maintaining the higher accuracy here. Especially in the larger models, like you have seen the results of the Quen model. It uh, it's it represents strong step forward in making the LLM more efficient in the reasoning task. Thank you.